Hello and welcome to a new video in a course on calculus. This video and the coming videos will be short videos where I'll discuss like convergence tests for infinite series. Now that we've defined infinite series and we've defined we've talked about the nth term test and the comparison test in the previous video. And I remind you, in the previous few videos, we've talked about infinite series, and we mainly discussed the nth term test and the comparison test. So I so I advise you to review what we've discussed over there. Anyway, in this video we will be discussing what's so-called the limit comparison test. So just as I mentioned for the comparison test, sometimes you have some knowledge of a convergent series, right? So sometimes you have a series, the sum of an from n equals 1 to infinity, and you have another series, the sum of bn from n equals 1 to infinity. So sometimes you know that some series is convergent. Let's say the sum of bn is convergent, like the bn is kind of like, it looks like it resembles the an. And for that we said that if we can find an inequality between these, it doesn't have to look like it, but there should be some inequality between these two, that should be obvious from looking at an. For example, if you can upper bound an by bn, and we've discussed some important conditions such as they have to be positive sequences. So we've discussed these in details in the previous video. So in this video, it's another tool for checking convergence of series. So I remind you real quick, so far the tools we have for checking convergence or divergence of a series are the following. So for convergence, we so far have the definition. We know that this series is convergent if the limit of the partial sum exists. So if this limit exists, and the partial sum, I remind you, it's the sum from n equals 1 to big N of an. So you take these partial sums and you ask yourself, is the limit, does the limit exist or not? Because remember, at the end of the day, a series is just a limit of the partial sum, right? This I've been stressing over and over again in the previous videos. So the first way of checking convergence is to check if the limit of the partial sum exists. The second way is the comparison test, that I'm gonna refer you to the previous video to see it. And these are the things that we had for checks of convergence, right? So for divergence, we had also two tools so far. So the first tool was also to check by definition, right? So since this series is actually a limit of partial sum of Sn, since this is defined to be the limit of Sn, if the limit of Sn does not exist or is equal to infinity, then the series diverges, right? So this was another tool for checking divergence of a series. So the next tool we had for checking divergence was what we introduced in the last video, which is the nth term test. So the nth term test is the test that says that if the series an from n equals 1 to infinity is convergent, then the limit of the ans as n tends to infinity must be 0, right? And I stressed enough that this implication, or this if-then statement is in this direction. Like, if it's convergent, then the limit must be 0. So we cannot use it to prove convergence of series. However, if the limit of an as n goes to infinity is not 0, so if we have a series and the limit of an is not 0, then we can conclude that the sum of an from n equals 1 to infinity diverges, right? So this nth term test is used to prove divergence of series. However, it's supposed to give you some feeling, because you get a series. The first thing you do is that you check the limit of the summand. You check the limit of the an. If the limit of an is not 0, then the series is divergent by the nth term test. If the limit of an is 0, then it gives you some sort of feeling that that maybe convergence might happen, but it's not quite a proof, right? So we're gonna add a new tool for this list. So let us do that. So the new tool for this list, it's gonna be the limit comparison test. So this is gonna be yet a new way of proving convergence of a series. And this is also gonna be a tool for proving divergence of a series. The limit comparison test. Okay, so now that we've kind of motivated what we're gonna talk about, let's talk about the limit comparison test. So the limit comparison test, here's what it says. It says that if you have two series, an and bn, and it must be that they're series of non-negative terms, series of positive terms, right? An should be non-negative, bn should be positive. It should happen for every n, right? And if we have that the limit of an over bn is equal to c, where c is a positive number and it's not equal to infinity, and I stress here it's a positive number, it cannot be that c is 0, for example, then both series converge or both series diverge. They converge or diverge at the same time. Okay, so it's a long statement. Let's break it down and let's understand it. Okay, so the best way to understand it, I guess, is to give an example. So let us do that, I guess. So here's an example. So let me remind you, recall, we have that the sum of 1 over 3 to the n, or let's say 2 over 3, just the sum of 2 over 3 to the n, as n runs from 0 to infinity, we know that that this is a geometric series, because recall geometric series take the form the sum of a times r to the n from n equals 0 to infinity. So this is a geometric series, right? And r here is equal to 2 over 3 and a is equal to 1. And I remind you, geometric series, recall, geometric series are convergent for r in absolute value strictly less than 1. Okay, so this is what we have. So if r is strictly less than 1, then the series that we have is convergent because it's a geometric series, and we've discussed this in a previous video. Okay, so here we have r is equal to 2 over 3. Well, r is strictly less than 1. Well, this means that this series is convergent because of this, right? Because of that thing. Because it's a geometric series with r equal to 2 over 3, which is strictly less than 1. So it's convergent. Okay? So this thing we know. Now, I ask you a slightly different question, and without the help of a comparison test, you would like, it's not gonna be very nice answering this question, right? So let me ask the question and then we're gonna answer it. So the question says, is the series the sum from n equals 0 to infinity of 2n plus n squared over 3 to the n, is this convergent or not? of course, you need to justify your answer. So you look at this series and you ask yourself, well, what can we do? Well, you look at this series and you ask yourself, well, how do we tell? Well, you need to try the convergence tests that you've learned so far, and you need to check if any of these work for it, if any of these works for it. And plausibly, it might be a divergent series, right? So the first thing I guess that we should start by doing is to check the nth term test, right? To check if the limit of this thingy is 0. Well, if it's not 0, then it's automatically divergent. If it is 0, then we have some hope, right? So let us do that. So what's the limit as n tends to infinity of 2 to the n plus n squared over 3 to the n? Well, you can break this down. Well, you can break this into the limit of 2 over 3 to the n, because you can group the 2 to the n over 3 to the n, and then you have the other limit, if you break the fraction, n squared over 3 to the n. N equals, n goes to infinity, right? So the first limit is something that we computed before. This is the limit of r to the n, where this is less than 1, is strictly less than 1. This thing, we computed it before, and we said that this is 0, right? Plus, now this thing is a bit of an ugly thing, and I guess now you're familiar enough now to use L'Hopital's rule, for example. L'Hopital's rule to prove this equals to 0, right? So this is equal to 0, but I remind you how to remember this. Remember that exponentials, so this exponential, and this is a polynomial. So remember me telling you that exponentials always beat polynomials, right? They're kind of stronger and faster than polynomials, right? So 3 to the n is going to infinity, n squared is going to infinity. However, 3 to the n goes faster than n squared to infinity, and thus it beats it and it makes it a 0, right? So I'm gonna leave it to you as an exercise to use L'Hopital's rule and verify that this limit is actually 0. So the limit of the overall thingy is actually 0, and this means that the nth term test doesn't tell us anything here, right? So it doesn't tell us, because if it were non-zero, then it tells us that it's divergent, but since it's 0, it doesn't tell us anything. So I guess the next thing to do, now that we have some feeling that this might be true, is to use some comparison test. So you ask yourself, can we use the comparison test? Like, can we get some inequality between this thingy, for example, and this thingy? Because we know that the above thing is convergent. So perhaps if we can kind of upper bound it by, like if we can have some sort of inequality that this thing is less than the thing above, then we can get convergence, right? But that's not immediately obvious. So you resort to our new tool, which is the limit comparison test, okay? So let me write things here. We have an equals to 2 to the n plus n squared over 3 to the n. So we're interested in the sum of this thingy, right? We're gonna call the thing here an, okay? And we know that the sum of this thing is convergent, so let us call this bn, right? So let us call bn to be 2 over 3 to the n, which is actually 2 to the n over 3 to the n. Anyways, so we know that the sum of bn from n equals 0 to infinity is convergent. So this we know because we discussed this. It's a geometric series, and with r strictly less than 1, and thus it's convergent, okay? So this thing we discussed. So we go back to the limit comparison test, and we look at what it tells us. Okay, so you have two series. One of them you know something about, and the other you don't, right? So in our case, we know that the sum of the bn's is convergent. And look at what the theorem is telling us. The theorem is telling us that if this thing happens, then both of the series converge at the same time or diverge at the same time. Right? So if you know that one of them is convergent, then the second must be convergent, right? If you know that one of them is divergent, the second must be divergent. If this thing is satisfied, if this bullet point is satisfied. So first of all, but just to be careful here, we have to have both of these non-negative. Well, do we have that? Well, sure, because this is actually positive, this is always positive, and this is always positive. Notice even if n is 0, right, this thing is gonna be 2 to the 0 plus 0 over 3 to the 0, which is thus plus 0 over 1, which is 1, okay? So this thing is always positive. Also, this thing is always positive, right? So the first check, or the first condition of the theorem, this thing is okay, okay? So let's see if the limit of an over bn is equal to some constant, right? And this constant is not infinity or 0. So let's see what this limit is. So let's take the limit of an over bn and see what that thing is, okay? So this is the limit of 2 to the n plus n squared over 3 to the n over, so there's a limit here, and tends to infinity, over the bn, which is 2 to the n over 3 to the n. Alright, so if we cancel the 3 to the n's, we get that this is the limit as n tends to infinity of 2 to the n plus n squared over 2 to the n. Right, so if you expand this now, we're gonna get that this is the limit as n tends to infinity. If you break the fraction, it's gonna be 2 to the n over 2 to the n at first, which is 1, plus n squared over 2 to the n, right? So the limit of 1 is 1, and the limit of this thingy is also 0, so exercise, just as the previous exercise, show that the limit of n squared over 2 to the n as n tends to infinity is equal to 0, and you may use, for example, you may use L'Hopital's rule is 1. Okay? So we just computed the limit of the ratio of an and bn, and it's a number that is between 0 and infinity. It's strictly bigger than 0 and strictly less than infinity, and thus so this 1 is between 0 and infinity, and so by the limit comparison test, what do we have? Well, we have that both the sum of an and bn, so this sum and this sum, converge or diverge at the same time. So this is what the theorem is telling us. But we know that the sum of bn from n equals 0 to infinity is convergent. So this thing we know, right? We know from here, because we know that this is a geometric series, just as we discussed over here, right? It's a geometric series with r strictly less than 1. And we know that the sum of bn is convergent. So since they both converge or diverge at the same time, then the sum of an as n goes from 0 to infinity is convergent. So the answer to this question is yes. Okay? So this is what we have. Okay. So we're gonna take an example of two series diverging at the same time now. Okay. So I give you this series, okay, and I ask you is this convergent? Well, you look at it and like it's not immediately clear what's happening here, right? It's just like it's just vague, right? You can't just tell from looking at it. You have to do something. You have to try the tests that for convergence and divergence that you have. But as you see, like you can't use the definition. You can't just look at the partial sum and like try to find whether or not the limit exists, because it's gonna be a mess, right? It's not very clear. If you sum this up to n and you call this Sn and you ask if the limit of this exists, it's not very clear whether or not it does, right? So this is not a good idea. It's not a good idea. So this is the first tool we had. Well, the second tool we had for checking that a series is convergent or divergent is to get some feeling if the nth term test gives divergence, then we're done. So let us see. So we have the limit of n plus 1 over n squared plus 1 as n tends to infinity. You want to check if this is not 0, then it's automatically divergent. So let us see. Well, the limit of this thingy is again like you can either use L'Hopital's rule or you can just divide. So here's a trick for you. I want you to keep track of this. So what we're gonna do is that we're gonna take the bigger term. So the trick is take bigger term out. So this is the trick. So what's the biggest term? What's the biggest power of n in what you see here? Well, it's n squared. So if we take n squared from below, we're gonna be left with 1 plus 1 over n squared, because we took n squared in common. Like if you expand this back, you get this thing, right? And from the numerator, what we're gonna do is that we're gonna also take n squared. We're gonna take the biggest term from both, right? If we take n squared from above, what do we get? Well, we get that this is gonna be 1 over n plus 1 over n squared. I hope that this is clear, right? We're just taking a common factor, like just pulling something outside. We have to divide by it when we pull it, but we have a n here, so we only divide by n, okay? So, and now you cancel the n squareds, and this is gonna be the limit of 1 over n plus 1 over n squared over 1 plus 1 over n squared as n tends to infinity. And you compute this limit, and you will see that this is gonna be the limit of 1 over n 0, limit of 1 over n squared is also 0, over 1 plus the limit of 1 over n squared, which is 0, and thus this is 0 over 1, which is 0, right? So the nth term test doesn't tell us anything here, because it just gave us 0, and when it gives us 0, it doesn't say anything, okay? So the next thing to try are comparison tests. So let us try whether the comparison tests work. We first have the comparison test where you need some inequality between this and between something that you know is convergent or divergent. Well, it's not also clear, right? It's not clear if you can get an inequality, right? So you look at this and you can't say much, right? But here's what I want you to think of, okay? So if you look at this summand that you have, if you ignore the ones, so when n is big, if we ignore the ones, like if n is big, let's say we ignore the ones, the plus ones, okay? If we ignore these, we have n over n squared, which is 1 over n, okay? So if we ignore the ones, we have 1 over n, okay? So this should tell you that this series is kind of similar to or behaves similarly to 1 over n, right? But this is not enough. This is not enough to verify that, right? But you got some feeling that 1 over n is something to compare with, right? It's a series to compare with, okay? But we know that the sum of 1 over n is divergent. So if you can use the limit comparison test and check the conditions of the limit comparison tests, then this series should behave just as this series, and thus it should diverge. So let us see what the limit comparison test tells us. So let's call this thingy Bn, and let's call this thingy An, okay? And again, here's the statement of the limit comparison test. You need to check that the limit of the ratio is equal to a constant that is not 0 and not infinity, strictly between these, and then both series that you have will behave similarly. They both converge or both diverge. And we need to check also that they're positive. So let us do that. So first of all, it's clear that this is positive. The An is always positive, right? We're just plugging positive n in here, and this is positive. And 1 over n is also clearly positive, right? So I'm talking about not the series here, but Bn, okay? So this thing is obvious, and this is happening for every n. Bn is positive for every n, An is positive for every n, and thus we can now check the conditions of the limit comparison test. If you take the ratio of An of this thing, if you take the ratio of An and Bn, okay, well, plugging things in, you have n plus 1 over n squared plus 1 over 1 plus n, 1 over n, excuse me, over the Bn, okay? And now, multiplying the far by far and the close by close, you get that this is n times n plus 1 over n squared plus 1, okay? So this is what we have, because you're multiplying n squared plus 1 by 1 in this case. Now, you need the limit of this, because if you get the limit of this, this is what's gonna tell you whether or not the limit comparison test can be applied or not, okay? So if you get the limit of this, you will see that the limit of this is actually 1. But why is that? Is there a quick way to see this? Well, sure. Though I expect you now to be good with limits, let me just remind you of how to do this. So you want the limit, let's expand this, okay? We want the limit of n squared plus n over n squared plus 1 as n tends to infinity. Again, when we have polynomial by polynomial, what we're gonna do is that we're gonna take we're gonna use this trick. We're gonna take the biggest term outside, or the biggest power outside, okay? So this is the limit. What's the biggest power in what we're seeing here? It's n squared. So let's take n squared above, and this is gonna be n squared. What's left inside is 1 plus 1 over n, okay? And below it, we take also n squared, and we'll be left with 1 plus 1 over n squared, okay? Canceling the n squared, right? What do we have? We have the limit of 1 plus 1 over n. The limit of 1 over n is 0, okay? So we have 1 plus 0, so on. And below, we have the limit of this thing, and the limit of 1 over n squared is 0, and thus we're left with 1 too. So this is 1 over 1, and this is equal to 1, just as we claimed. And this number is between 0 and infinity. 1 is strictly between 0 and infinity. And thus, since this thing diverges, it's necessarily the case that this thing diverges. Why? Because by the limit comparison test, they both converge or diverge at the same time. So that's it. We just proved that this ugly series is divergent.